7 8 joints and 1 joint.
I remember we like 2 years ago, and then after the awkward thing, there was like half and half.
Yeah, no. I would take like, haircuts to get it out. And then I got it.
I remember from my mom, like, they all the water, and be like, "Are you sure?"
Yeah.
Like, yeah, it was so short. It was good. It was good.
It used to be peace actually.
I was
Faded as well.
Yeah, mine, I did bleach without any toner, so it came out orange. Yeah. Yeah,
so I had a little bit.
I never had.
The highest one was still.
Walking around is fine.
I hear the intro and then
As you walked up and
yeah, right.
Yeah.
I like for the
Here longer.
couple weeks. Yeah, it was like a couple weeks I had it. So yeah. It sounds like
Yeah.
a big social.
Yeah. Yeah.
Mostly like. Actually, like a big. It says what you mean. I'm fine every night.
But that's not as well now. Yeah.
We're also like at the end, they call. I like it, I can copy paste a little. You just feel like.
Yeah, I got like back to back classes today. Yeah, now I got like full day this class. And my Tuesday, Thursday.
The same.
Yeah.
Idiom. And
11:30.
Thank you.
So 11:30,
Yeah.
2:30, 4 o'clock. I think. 4 o'clock.
All right, it's 4 o'clock. Let's go and get started.
Yeah, another one.
All right, good afternoon, everyone. How's everyone doing today? Good. Good to hear. It got kind of cloudy and cold on us all of a sudden. So yeah, hopefully maybe it might seem like rain's coming.
Hopefully. Sunshine Texas.
I know we're paying for sunshine, we should get it. All right, so plan for today is we're going to finish up our lecture notes on second order ODE. So this is the last day that I had planned for this stuff. So we have one more example to do with undetermined coefficients. Kind of like a little bit of wrinkle in terms of, something that can happen in certain situations. And then we'll use that to kind of springboard into our final topic, which is this idea of resonance, which is a very important topic for just engineering in general, especially if you're in designing structures of some kind. But every engineer should know about resonance. Okay. All right. announcements. So remember that homework 2 is posted. After today, you should have everything that you need to do homework 2. Because next week we are starting a brand new topic, which is Laplace transforms, right? So this kind of marks the end of, I would say, kind of the review portion of 308. So, I think a lot of what we've covered so far, I think a lot of people have kind of seen these in some capacity in their previous math classes, but Laplace transforms are kind of when we start to kind of diverge and kind of start to do some new stuff. So, I know the pace in the class has been pretty fast until this point, but next week we'll start to slow down a little bit, just because this is that's Laplace is kind of more newer stuff, I think, for most people. Okay. All right, any questions I can answer before we get started for today? Yeah.
On Tuesday, we had gone over plugging the guess back into the original ODE. Are we gonna be able to elaborate on that one a little bit?
Yes, yeah. So we'll go over kind of, we kind of went over undetermined coefficients just for one example, but we'll talk about it more in general today. And we'll do one more example to kind of show that. Yeah. Mhm. Okay, all right, so let's go ahead and get started. Okay, so we were talking about undetermined coefficients. For non-homogeneous solutions. Okay. So last time we started talking about the solution to non-homogeneous second order ODEs, right? So let's just remind ourselves exactly what that means. Okay. So we have a second order ordinary differential equation, d squared y dx squared plus p, sorry, my brain is a CFD pilled right now. So dy dt plus qy is equal to r of x. Okay. So a non-homogeneous differential equation basically means that the right-hand side of our equation, which is that r of x, is non-zero. Okay. So just by this existing means that we have a non-homogeneous equation. Okay. All right, and so the idea with undetermined coefficients is that, if we were going to solve for the particular solution to our differential equation, that's particular to that non-homogeneous part, basically we're making the assumption that our particular solution is going to take the same functional form as our non-homogeneous part. So that's kind of the whole idea with undetermined coefficients, right? So we guess a form for our particular solution. It's going to have the same functional form as r of x. The only difference is that, we're going to have undetermined coefficients in our guess. Okay. So last time we did an example with a with the polynomial forcing function, right? R of x was just some quadratic function. We can use undetermined coefficients for a bunch of different functional forms. So I thought I'd start today by giving you a table to kind of help you organize to see if your R of x function has this form, this is what your guess should look like. Okay. All right, so this table on one column will have R of x, okay? just for trivia purposes, we'll give the name of this type of function. And then on the right-hand column here, we'll have our guess for the particular solution. Okay. So let's start with the one that we already saw, which is a polynomial function, right? So a polynomial function is basically any function of x raised to some integer power, right? So x to the n. So this we call a polynomial, right? Where n is some integer. Okay. And by the way, we can have some lower order terms too, but we're only looking at just the highest order polynomial terms, right? And then the rest can kind of work themselves out. Okay. And so our guess for YP in this case, remember, is a full polynomial of the same order. And what that means is that, we include a polynomial term of the same order n, but we also include all the lower order terms as well. Okay. And so what this looks like is kn x to the n plus kn minus 1 x to the n minus 1 plus ... plus k1 times x plus k0. Okay. Including all the lower order terms is really important, right? So if you remember from our example last time, our R of x was simply just some, I think it was like 0.001 x squared. But even so, we included the linear term in our guess as well as our constant term. And what we found was that, our constant term was non-zero, right? So it's important to include all of the lower order terms. Otherwise, you're not going to get a solution. Okay. Okay. All right, next, the next type of function that we can use undetermined coefficients for is an exponential. Okay. So our R of x in this case is some e to the alpha x. Okay. So this is just a simple exponential function. Okay. Okay. So for exponential functions, our guess for YP is pretty straightforward. We just take an exponential of the same function with the same exponent, except we just add an undetermined coefficient. Okay. Okay. All right, next we have a sinusoid. So that's probably the next most common one. So let's say we have cosine omega x and or sine of omega x. Okay. So this is we call these sinusoids. Okay. Now, sinusoids kind of work similarly to our polynomial. So whether we have just cosine or just sine, our guess for YP has to include both sine and cosine. Okay. Right. So our guess for YP is going to be, we'll say K1 cosine omega x, okay, plus K2 sine omega x, okay. And so I'll leave a note here, must always include both. All right, so technically speaking, these three cases these are kind of our building blocks. But you can also have combinations of these as well. So you can have like an exponential multiplied by a polynomial, or an exponential multiplied by a sinusoid. Okay. And so in those cases, you more or less kind of follow the same rules. But just to kind of illustrate to you, let me just kind of show you probably one of the more common ones that you'll see, which is the decaying sinusoid. Okay, so these are situations. Okay, so actually, let me put a line here, just because everything above this, that's kind of our base cases. Okay. All right, so you might see a special case where maybe you have like e to the minus alpha x sine omega x. Okay. And or e to the minus alpha x cosine omega x. Okay. All right, so you have the product of basically an exponential and a sinusoid. Doesn't necessarily have to be negative. It's just that for the most part, you're going to see negative. Uh, if you're using these to represent physical systems. All right. And so in these cases, you follow basically the exact same rule. So like, the exponential part, your guess for YP has to include an exponential with the same exponent. And then for the sinusoid, you have to include both sine and cosine. Okay. And so your guess has to be e to the minus alpha x multiplied by k1 cosine omega x plus k2 sine omega x. Okay. Right. We basically maintain that same functional form while still kind of obeying the rules. It does get a bit complicated when you have products of different functions. And so, when you have like a polynomial and a sinusoid, those are not fun problems to do. But technically you can do that from it's just that you would have a ton of different coefficients to consider. Okay, so I would definitely keep this table handy. I believe so. So for the first midterm, I am going to give you guys a formula sheet. And so this will be on the formula sheet. So, don't worry about. So I think some people have asked already, but for my midterms, I'll let you guys write your own kind of sheet of notes for the exam. But this you don't have to write down. This will be provided. All right. Any questions on this so far? Okay. All right. So undetermined coefficients, interestingly, I think is actually fairly straightforward. You just, look at the functional form and then you can make your guess and just plug in from there, right? It's not that complicated, but it does get very tedious sometimes for certain functions. Okay. The only additional thing that we really have to talk about is some special cases. Okay? So remember, when you're solving a non-homogeneous ordinary differential equation, the first step is always to solve for the homogeneous solution, right? And so a special case can occur when your homogeneous solution and your guess for the particular solution have the same functional form. Okay. Because if you notice, maybe not so much for the polynomial, but for the exponential and the sinusoids, right? If you think about how our solutions look like for our three cases for, if we had two distinct real roots or complex conjugate roots, critical damping, right? Those functions have those exact forms, which are exponentials and sinusoids, right? So it could happen. In fact, it does happen actually quite a bit where, those have the same form. And you can't have that, remember? So remember, we've already discussed that. When you're making a solution to a differential equation, the different terms or the different components of your solution, they have to be linearly independent of each other. Okay. And so we need a solution here, right? So we need to do something to make our particular solution unique. Okay, so to make our particular solution linearly independent, we're going to rely on the same trick that we had when we had our repeated root. So we're simply just going to multiply by x or multiply by t, whatever our independent variable is. Okay, so this is the same. And just because we didn't really have the chance to formally prove it, so I'll call it trick, right? So it's the same trick that we use for our repeated roots. Okay. All right, so let's do an example that kind of shows this, right? So I think this example will be a good chance to kind of show what that looks like, as well as kind of giving you another look and seeing how undetermined coefficients work just in general. But any questions on anything before we jump into that example? Okay, all right, let's go ahead and jump in. Okay, so let's look at the following example here. So we have d squared y dx squared plus 3 dy dx plus 2.25 y is equal to minus 10 e to the minus 1.5 x. Okay. All right, so we have a non-homogeneous second order ordinary differential equation as evidenced by the right-hand side being non-zero. Okay. I don't think in this one, I don't have any initial conditions for you guys. And so for this one, we're just going to solve for the general solution. Okay. All right, so let's go through our procedure, right? So remember, first thing we always do when we have a second order differential equation, whether we have a homogeneous problem or not, right? We're going to solve for the homogeneous solution first. Okay. So our homogeneous problem, we're basically going to ignore the right-hand side. We're going to set it equal to 0. So you have d squared y dx squared plus 3 dy dx plus 2.25 y equal to 0. Okay. All right. Now we can form our characteristic polynomial. So we have lambda squared plus 3 lambda plus 2.25 is equal to 0. Okay. All right, so just like we usually do, we can plug this into our quadratic equation, solve for the roots of this characteristic polynomial, okay? Just for the sake of time, I know it's only going to save like a couple minutes, but I'll just go ahead and give you the roots, right? So in this case, we actually have a double root, and so we have two roots that are in the same place, okay? Okay, and so we get lambda is equal to minus 1.5. Okay. So basically, this function here factors as lambda plus 1.5 squared. All right, and so now that we have our homogeneous, well, we have our roots, we can go ahead and form our homogeneous solution, right? So for repeated root, remember the way that we do this is that we take one exponential function, and then the other exponential function we multiply by our independent variable. So we have YH of x is equal to C1 e to the minus 1.5x plus C2. For C2, we're going to multiply by x. So C2x e to the minus 1.5x. Okay. All right. All right, so at this point, second order ordinary differential equations, constant coefficients, homogeneous should be, start to become second nature to you guys, just because we've seen so many of these. All right, so now that we have our homogeneous solution, the next step is to solve for the particular solution. Okay. And of course, the method that we're going to use for this is undetermined coefficients. Okay. So let's look at the form of our non-homogeneous terms. So our non-homogeneous R of X is equal to minus 10 e to the minus 1.5 x. Okay. So right away, when we see this function, we can see that it is an exponential function. Right. So that tells us right away that our guess for our particular solution is also going to be an exponential function with the same exponent. Okay. So let's guess yp of x is equal to c. Well, let's use a different letter. Let's use k, because we use c for the general solution. K e to the minus 1.5 x. Okay. Okay. All right. So normally at this point, you could take your guess for your particular solution, plug it back into our original differential equation, perform the derivatives, and then use that to solve for the coefficient, right? Unfortunately, we can't do that in this case, because if you look at our form here, right? Our form for yp is just e to the minus 1.5 x, right? Where have you seen that before? Okay. Well, turns out our homogeneous solution has that exact same functional form, e to the minus 1.5 x. So our particular solution cannot take this form because it's part of the homogeneous solution. Okay. And so what should we do in this situation? Well, the only thing that we can do, which is just multiply by x, right? So let's try that. So let's do guess 2. Okay. So we have yp of x is equal to, same thing, except we're just going to multiply by x. So kx e to the minus 1.5 x. All right, good. Well, unfortunately, we're still have an issue, because if we look at this functional form, x e to the minus 1.5 x, well, turns out the other part of our homogeneous solution has the same functional form. Okay, so we still can't use this. Okay. So this is still part of YH, so we still can't use it, right? So what do we do from there? Well, if at first you don't succeed, then just try again, right? So let's do that same thing again. Let's multiply by x one more time. So let's have guess number 3, parentheses, this time for sure. Okay, so we multiply by x one more time. We get yp of x is equal to k x squared e to the minus 1.5 x. Okay. All right, so let's check one more time to make sure that this is not part of the homogeneous solution, right? And it's not. So we are good to go. All right. So we're finally ready to move on. We have a form for yp that's not part of our homogeneous solution. Okay. Now, this is kind of an unusual case. Normally you don't have to multiply by x twice, but just know that you can keep kind of multiplying by x until you get something that's unique. Okay. All right, any questions on this? Okay. All right, so now that we've settled on a form for our particular solution, let's go ahead and plug this back into our differential equation and solve for the coefficient. All right. So unfortunately, when you do multiply things by x, you do get kind of a product function. And so in order to take derivatives, we do need to use some product rule. Okay. Okay. So let's go ahead and do that. So we have yp is equal to kx squared e to the minus 1.5x. Okay. Let's take its first derivative. So let's take dyp dx. Okay. Is equal to. So the k is just going to be out in front. It's going to multiply the entire thing, right? So we're going to take derivative of the first, which is 2x, e to the minus 1.5x minus 1.5 x squared e to the minus 1.5x. Okay. So that second term is the derivative of the second part, which is e to the minus 1.5x. Okay. So we get a minus 1.5 that comes out in front. The x squared stays the same. And the derivative e to the 1.5 negative 1.5x still stays e to the negative 1.5x. Okay. Okay, so let's take another derivative. So d squared yp dx squared. Okay. Okay. Now we got to apply product rule twice, right? So we got two terms that came out from the first derivative, and each of those are products. We have to kind of do product rule again. Okay, so we're going to take first derivative of 2x e to the minus 1.5x. Okay. So that is going to be 2 times e to the minus 1.5x minus 3x e to the minus 1.5x. Okay. All right, so that one term kind of became these two after we took the derivative. Okay. And then next we have this term right here, right? So this is also going to split into two just from the product rule. Okay. All right, so first we have minus 3x e to the minus 1.5x. Okay. And then we have plus 2.25. So that's 1.5 times 1.5. That is 2.25. Okay. X squared e to the minus 1.5x. Okay. All right, so let's go ahead and simplify this because we can see here that we have two terms, minus 3x e to the minus 1.5x. We can kind of combine those. And so if we simplify this, we get d squared yp dx squared is equal to k times 2 e to the minus 1.5x minus 6x e to the minus 1.5x plus 2.25 x squared e to the minus 1.5x. Okay. All right. So it's a little bit cumbersome with the product rules, but we're there. So now that we have the derivatives, we can go ahead and plug these into our original differential equation. Okay. So we're going to plug this in. We're going to plug this in. Okay. So let me go ahead and write down our original differential equation one more time. And this time we are going to include the non-homogeneous term on the right-hand side. Okay. So we have d squared y dx squared plus 3 dy dx plus 2.25 times y is equal to minus 10 e to the minus 1.5 x. Okay. All right, so we're going to go ahead and plug in for basically everywhere we see y. Okay. All right, so first the second derivative, we actually have that conveniently right there. So we plug in for the second derivative, we get k times 2e to the minus 1.5 x minus 6x e to the minus 1.5 x plus 2.25 x squared e to the minus 1.5 x. Okay. All right. Now let's go ahead and plug in for the first order derivative. So the first order derivative, we're going to multiply by 3. So this is going to be plus 3 times k multiplied by, we have 2x e to the minus 1.5 x minus 1.5 x squared e to the minus 1.5 x. Okay. Okay. And then finally, we have 2.25 times y. So that's going to be plus 2.25 times k x squared e to the minus 1.5 x. Okay. Right, and all this is equal to minus 10 e to the minus 1.5 x. Right. Yep. Yep. So a lot of terms are going to cancel out, and that's kind of how you can check your work in these problems. So basically everything that's not on the right-hand side should cancel out. So everything that's x e to the minus 1.5 x and x squared e to the minus 1.5 x, those should cancel out because there's no way you can equate those to the right-hand side, right? If those don't cancel out, then I would go back and check your work. Usually there's some kind of some kind of mistake there. Okay. Okay. So let's go ahead and distribute all of our coefficients on the left, and then let's go ahead and simplify. Okay. So on the left-hand side, we have, I'm just going to take the k, and we're going to distribute this all throughout. Okay. So we have 2k e to the minus 1.5 x minus 6k x e to the minus 1.5 x plus 2.25 k x squared e to the minus 1.5 x. Okay. Right. Next, we have the 3k term. So we're going to distribute this 3k into this term and this term here. Okay. So the plus 6kx e to the minus 1.5 x plus, or excuse me, minus. Be careful of your negatives, especially if they're hanging out from the previous line. So minus 3 times 1.5, that's 4.5 k x squared e to the minus 1.5 x. Okay. And then finally, we have our single term here. So that's a plus 2.25 k x squared e to the minus 1.5 x. Okay. And all that's equal to minus 10 e to the minus 1.5 x. Okay, so let's go ahead and combine like terms here, and then hopefully we see that everything cancels as it should. Okay. First thing we're going to look at, let's look at the x term. So let's see, we have a minus 6kx. We have a positive 6kx. And that's it. So those two terms are going to cancel out. So we are all Gucci on that one. Okay. Next, let's look at the x squared term. So for x squared, we have a positive 2.25 kx squared e to the minus 1.5x. We have a positive 2.25 kx squared e to the minus 1.5x. And then we have a minus 4.5 kx squared e to the minus 1.5x. Okay. 2.25 plus 2.25 is a positive 4.5. And so those terms are going to cancel out as well. Isn't that so satisfying? You know, you do all this work and then a lot of it when you cancel that, you end up with something satisfying. It's like, very oddly satisfying. Okay, so all we're left with here is 2k e to the minus 1.5x is equal to minus 10 e to the minus 1.5x. Okay. All right, we can see that the e to the minus 1.5x, we can kind of factor those out and cancel them on both sides. And so all we're left with is 2k is equal to minus 10, which very easy to see is k is equal to minus 5. All right, and so after all that, we finally have our solution for yp. So yp is equal to minus 5x squared e to the minus 1.5x. All right, and so now that we have that, we can go ahead and form our full general solution, because our general solution, remember, is the sum of our homogeneous solution and our particular solution. So y of x is equal to yh plus yp. Okay. So yh, remember, is c1 e to the minus 1.5x plus c2 e to the minus 1.5x. And then we're going to add to that our yp that we just found. So minus 5x squared e to the minus 1.5x.
X behind the C2, right?
Yes, there is. Thank you. Yep. Mhm. All right, so that's that problem, right? So again, this one was a little bit unusual because we had to, first of all, we had a repeated root, and then our particular solution had the exact same form as our original one. But hopefully this kind of gives you a good idea in terms of what you should do, if you have to multiply by x. Okay. Any questions on this example here? Okay. All right, one final note before we move on to resonance is that, so I think for both the problems that I gave you for undetermined coefficients, I did not give you any initial conditions. So in reality, you can get initial conditions when you have a particular solution. Okay. So if you're given initial conditions, and of course, those initial conditions will be used to solve for the coefficients C1, C2. Okay. And so if you're given initial conditions, you have to wait until after you solve for the particular solution before you apply. Okay. So it's very tempting when you're doing these problems, right? So, for these non-homogeneous problems, essentially we follow a three-step process, right? So step one is to solve the homogeneous problem. Step two is to guess. Step three is to plug in, right? It's very tempting when you have initial conditions to plug them in right after step one to just the homogeneous part, right? But if you have a non-homogeneous problem, that particular solution also is part of your general solution as well. And so if you apply the initial conditions early, you try to solve for C1, C2 before you solve for the particular solution, you're not going to get the right result. Okay. So do not apply okay. It's tempting. And and I think, and honestly, I think that just comes from muscle memory, just because we've done so many homogeneous problems up to this point. I think it's just kind of if you're not really kind of thinking about it, you find the homogeneous solution, you see some initial conditions, and so you just kind of go for it, right? But if you have a particular solution, you have to wait until after your particular solution is formed, you get the full general solution, then you can apply it in the initial conditions. Okay. So just kind of one thing to be careful about, because there are problems like that in the homework. And so you want to make sure you wait until after your particular solution before you apply the initial conditions. Okay. If you think about it from this perspective, that the initial condition should always be the last thing that you do in a problem, then I think it helps to kind of remember that step. Okay. You should never apply initial conditions somewhere in the middle of your problem. It should always be kind of the last thing. Okay. Any questions on this? Okay. So, unfortunately, that's all we have time for in terms of examples for undetermined coefficients. I do have at least two more examples in the notes. It's just that, these problems kind of take a while to kind of go over in the class. And so, I have to make sure I cover resonance right now before we move on to Laplace. So if you do want to see more examples, in my lecture notes, I do try to be as detailed as I can in terms of writing out every single step. I try not to leave anything out. So, definitely check out the notes. If you do want to see a couple more examples. So the other examples I have in the notes are definitely a bit more, there's more steps involved in them. And so, that's also part of the reason I leave them out of the lecture. But I definitely do encourage you to check them out if you do want to see more practice. Okay. Okay, but for the last 30 minutes of class today, I do want to shift gears and talk about this concept of resonance. Okay. All right, so resonance is a very interesting phenomenon. In fact, a lot of, I would say, just a lot of the really eye-catching kind of, videos that you might see on the internet of like, look at this cool science thing. A lot of them have to do with resonance, right? Because resonance kind of is always kind of displays this kind of behavior that you don't really expect from a given situation. Okay. So let me start by saying this, right? Every physical object in the world has something called a natural frequency. Okay? All right, so what is the natural frequency? Well, the natural frequency can mean a lot of things, but for the sake of argument here, a natural frequency, you can think of it as the frequency at which an object prefers to vibrate, okay, if it were perturbed. So this idea of natural frequency, I think, is most clearly kind of illustrated when you think of the idea of a musical instrument, right? And so the easiest kind of way to kind of illustrate this is with a guitar, right? I guess more specifically, the strings of a guitar. Okay. All right. So guitar, guitar, every musical instrument is complex and interesting in its own way. So, I by no means am I kind of oversimplifying, guitars here, but a guitar, or at least the strings, are basically just, wires or these kind of very thick strings that are pulled very taut, right? So they have a lot of tension. Right? And so the way that guitars generate music is that if you pluck the string, so let's say that you take your finger and you kind of pluck it, right? You basically just you take it and you pull it up a little bit and then just release, right? And so if you do that, what you should observe is that the whole string is going to vibrate, right? Okay. Right? And oftentimes that vibration happens very fast that you can't really perceive it with your. I mean, you can see the string moving, but it's hard to count exactly how fast it's vibrating, right? But believe it or not, that string is actually vibrating with a single frequency. So basically the frequency at which the string is going up and down is going to be constant, right? Because that's the natural frequency of the string. And how do you change that natural frequency? Well, natural frequency kind of depends on a lot of different factors. And so the most prominent are usually geometry, right? And so if you have a thicker string, a thinner string, longer string, shorter string, it's going to produce different sounds. And so that's kind of the idea of all the different string instruments, right? So we look at compare like a banjo to like an electric guitar, regular guitar, right? All of those have different tensions, different size of the string, different lengths. And so they all produce different sounds, right? But strings are not the only things that have natural frequencies as well, right? If you look at any object in this room, they all kind of have their natural frequency. It's just that oftentimes it's much harder to perceive than a string. Okay. Now, we're talking about natural frequency here in terms of what I call kind of impulsive loading, where if you hit it or you pluck it and then you kind of let it go on its own, right? But a really interesting phenomenon happens if you apply persistent loading or persistent forcing to an object at or near its actual frequency, its natural frequency. Okay. Okay. So if we apply persistent loading to an object at its natural frequency, this is what causes resonance to occur. All right, so to kind of illustrate that and to kind of, kind of leave a little bit of a cliffhanger, right? Because you might be asking, what happens when resonance occurs? Well, let's look at a very simple mathematical example to kind of illustrate to see what would happen. Okay, so let's do a very simple example. So let's kind of go back to our analogy of the mass spring damper, and let's look at a situation where we have an undamped oscillator. Okay. Okay, so let's say that we have an object that it has this following differential equation. So we have d squared y dt squared, okay, plus 4y is equal to cosine 2t. Okay, so the reason I'm calling it undamped is that you can see there's no first order derivative term. And so that, remember, that's that term that represented our damping in our mass spring damper. Okay. And then we actually have a non-homogeneous term as well. Okay, so fairly simple equation, but let's go ahead and solve for its solution. Okay. Once again, I'm not providing you any initial conditions here, but you know it's not going to matter. You'll kind of see in a second. Okay. Okay. First step, let's go ahead and solve the homogeneous solution. Okay. So let's form our characteristic equation. Lambda squared plus 4 is equal to 0. Okay. Here we have obviously a complex root, and so lambda is equal to plus or minus 2i. Okay. So this tells us that our homogeneous solution, YH of t, is equal to a cosine of 2t plus b sine of 2t. So we have these kind of undamped sinusoids, and so they're going to oscillate in time, but there's no damping component that's going to bring it back down to 0. So essentially, these are going to just oscillate and vibrate just forever. Okay. Okay. Now let's bring in the particular solution. So since we have that cosine 2t, let's bring that in. Okay. All right, so step 2, let's go ahead and guess the form for our particular solution yp. Okay, so our non-homogeneous part here is cosine 2t. That means our particular solution has to be a sinusoid of the same frequency, right? So we have yp is equal to k1 cosine 2t plus k2 sine 2t. Okay, so this is our guess based on form of R of x. Okay. Well, unfortunately, there's a problem with our guess. It's the same problem that we had in the previous example, right? Our guess for YP has the exact same form as our homogeneous solution, right? And so we can't use this because they have to be, they have to be linearly independent from each other. So let's go ahead and make another guess. Okay. So for guess 2 here, we're going to do the exact same trick that we did before. We're just going to simply multiply by t. Okay. So you have yp is equal to k1t cosine 2t plus k2t sine of 2t. All right. So that's good. So now we are good to go. So our particular solution is unique from our homogeneous solution. And so we can go ahead and move forward with this for our solution. Okay. Okay, so step 3 is to plug this back in. Okay. So we're going to take this particular solution and plug it back into our original differential equation. Okay. But before we do that, let's take a minute and kind of pause and look at our YP, because we have something here that we've kind of never seen before in our solutions. Okay, so let's pause for a second. Okay, let's take one of these functional forms here and let's examine it a bit more closely. Okay, so let's look at this k1t cosine 2t. And in fact, we'll forget about the k1 because the k1 is just a constant. We don't care about that. Okay, so we have t cosine 2t. Okay. All right. So we have the product of t being a linear function, that's just going to be something that increases linearly as a function of time. And we have cosine of 2t, which is an oscillatory sinusoid. Okay. So this function t grows linearly as t gets large. Okay. And this cosine 2t here, this is going to be an oscillatory function. So this oscillates in time. Okay. So just like we saw with our decaying exponential, right? So when we saw our decaying exponential multiplied by sinusoid, we saw that the decaying exponential had an effect of reducing the oscillations of our sinusoid. So let's see what happens when we multiply by a function that grows instead of decays. Okay, so let me go ahead and draw a coordinate axis here. So this is t, and on the y-axis, we're going to say that's going to be t cosine 2t. Okay. Okay. So first thing I'm going to do, I'm going to draw the function of t. And so that's going to be just simply a straight line. Okay. Right, so this dotted line here, this is going to be our function t. So y is equal to t. Okay. So you can think of that t as kind of a modulation of the amplitude of our oscillation. Okay? So we have a situation where our oscillation magnitude is actually going to grow with time. Okay? All right, so if we actually plot this out, it's going to look something like this. So it's going to start at nothing, but then eventually, you know, that function is going to grow. Okay. Right, so I ran out of space on the paper there, but you can imagine that this oscillation magnitude is going to keep growing and growing and growing. Okay. So this we call this like a sinusoid with a growing amplitude. Okay. How much is it going to grow? Well, how much does the function y of t grows? It grows unbounded, right? So as t gets larger and larger and larger, you know, t also, you know, the function y of t also gets larger and larger and larger, right? And so that means our sinusoid is also going to have its amplitude grow unbounded. Okay. Okay. So on the one hand, that's cool, right? And so, you know, even from a very simple kind of differential equation with a simple kind of forcing function, you know, we get this kind of cool result. But you know, besides cool points, you know, if you're designing an engineering system that is going to have an oscillation that grows unbounded, that is something that usually is very, very, very bad. You do not want to have unbounded oscillations, right? So this is basically what happens when resonance occurs. Okay. So when resonance occurs, okay, when resonance occurs, the way that it manifests or the way that you kind of observe it is that your physical system will have these uncontrolled, unbounded, large amplitude oscillations. And then from this example, we can kind of see exactly when that occurs, right? And so resonance can happen when you force your system at a very particular frequency, right? And what frequency is the bad frequency, you say? Well, if you look back to the start of our discussion, right? We said that every object has some natural frequency that it likes to vibrate. Okay. And so what the idea of resonance is that if you take your physical system and you apply some persistent loading, some persistent oscillatory loading that has the exact same frequency as the natural frequency, you are going to cause resonance to occur. Okay. So resonance is if you're going to be doing any kind of structural design of any object, you always need to be aware of resonance and how it can occur. Okay. And you'll be surprised that there's a lot of oscillatory loading that's out there that you wouldn't even consider, right? Right. I'll give you kind of a very example that if you're into cars, you'd be aware of this, right? And so if you're designing let's say parts on an engine, right? So an engine is known for rotating very fast, right? So you always characterize an engine by its RPMs, right? So that's how fast basically the shaft can rotate, right? So that rotation of that shaft actually causes an oscillatory loading based on the measured RPM. So if you're designing a component for an engine, right, you have to be aware of what range of RPMs that the engine is going to be expected to operate at, and you want to design your part so that it's not going to resonate at any of those frequencies. Another example. So, oftentimes, if you're designing a very large structure like a building or a bridge of some kind, right? You're gonna receive some kind of vibrating loading just simply from the wind, hitting your structure and causing some aerodynamic flutter. Okay. Circuits as well, right? So for the electrical engineers here, right? So if you're designing circuits, right? And so you're choosing components like resistance, inductance, capacitances for your circuits, right? You want to make sure that you don't get resonance if you're designing, say, like an AC circuit, so alternating current. You want to make sure that you don't have no risk of resonating based on your selection of components. Okay, so there's so many examples out there of resonance, and you know, it's something you kind of always have to be aware of if you're an engineer of almost any kind. So I would say almost any kind of engineer has to deal with the resonance of something. Okay. So what does that mean exactly? So how do you design your structure away from it, right? Or I guess maybe the better question to ask is, you know, what factors kind of go into determining the natural frequency? Well, the unfortunate thing is that, you know, unless you have a very simple object, unless you have like a guitar string, natural frequency is actually very difficult to determine precisely for an object. Okay. Most of the time, you're going to need some kind of computer tools to help you. And so, you know, if you know, for you know, my mechanical engineers that's going to be taking electives next year, you know, if you take finite element analysis, you'll see that there's a tool and a lot of FEA softwares like you can determine natural frequencies. Okay. But the kinds of things that go into it are things like the object geometry. Okay. The object mass. Okay. Object stiffness. Right. So whatever type of material it's made out of, whatever if you have springs to stabilize it, things like that. Okay. And of course, damping as well. And there's more, but I would say these are kind of the predominant characteristics. So if you look at the last three, so I mentioned geometry first, because most of the time geometry is going to be your predominant property that's going to affect your natural frequency. But if you look at mass, stiffness, and damping, right? Remember, these are the components of our mass spring damper. Okay. And so, in fact, you know, if you go through the kind of whole derivation in the notes, and so, you know, what I'm giving you right now is kind of a I would say kind of a qualitative explanation of resonance, but I do have some proofs and derivations in the notes, right? So in the notes, what you'll see is that I actually go through a whole derivation of a general mass spring damper, and I can basically show you that the natural frequency, you know, depends on the whatever values for mass and the spring constant K and the damping constant B. Okay. So a lot of times, you know, when you're designing structures, a lot of it is kind of tweaking the mass, tweaking the stiffness, tweaking the damping in the system so that you avoid resonance in certain areas. Okay. So actually, one thing that I think you should look at that's actually really cool. Okay. Not that this is a requirement, I think it's just a really cool application of this. And so you should look up the building Taipei 101. Okay. So if you don't know what Taipei 101 is, Taipei 101 is this skyscraper that's in Taiwan, it's in Taipei. Okay. It used to be the tallest building in the world, but then I think it was only the tallest building for like 14 days or something like that. And then Dubai built a bigger one. That's kind of the thing with human nature, is we're all trying to one up each other, right? But there's a very interesting design feature of Taipei 101 that kind of factors into our discussion here, right? So if you look down the middle, so Taipei 101 is this kind of huge skyscraper, but, you know, for the top, you know, I don't know, like, you know, top half of the building, the entire middle of the building is almost completely hollow, with the exception of this massive counterweight. Okay. So that counterweight serves quite a few purposes, and it's not as simple as just preventing resonance, right? Because one thing that happens in Taiwan a lot is they get a lot of earthquakes, right? And when an earthquake happens, you know, generally you don't want your massive skyscraper falling down and you know, destroying the other buildings, right? And so the way that the engineers designed the buildings was they had this massive counterweight so that, if an earthquake does occur, right? This counterweight kind of alters the properties of the building so that it does not resonate with the frequencies of the earthquake. Okay. And again, that's not the only purpose of the counterweight. So the counterweight is designed in a way so that if the building does, vibrate because of an earthquake, then that counterweight is going to take up most of that energy, right? So it's more complex than just making the building heavier, because there's other ways to make a building simply heavier. But that's kind of one of the nice side effects, is that it does make the building a lot more heavy. And then that does alter its natural frequency, so that if an earthquake does occur, it's still going to cause damage, but it's not going to be as catastrophic as if resonance occurs. Okay. If you're designing a skyscraper, which is this very tall, thin building, you are very susceptible to resonance and earthquakes. And so you have to design some kind of way for that building to kind of absorb those oscillations. Right? That's part of the reason you don't see massive skyscrapers in LA too, is because it's hard with all the earthquakes that we get. Okay.
Sort of and down.
Exactly. Yeah. All right. So that's resonance. So I believe the last problem in the homework kind of asks you a question on that. But at its core, resonance is only occurs if you have a mass spring damper system and you force the system, you apply a non-homogeneous term that has the same frequency as the natural frequency. Okay. All right. Any final questions before we wrap it up for today? Okay, all right, so that's all we got time for today. And so when we come back on Tuesday, we'll be moving on to Laplace transforms. So the first, I would say, true new topic of this class. Right? So thank you guys for coming this week. Hope you guys have a good rest of your weekend, and I will see you on Tuesday.
Ask you about the senior project thing.
Okay, sure.
I have an idea of what I want to do with it, but what's kind of the best way to go so that it's not just I built a drone.
It's you have to think about kind of application in terms of like what it's going to be used. And how you're going to, so I mean, when you're building a drone, there's there's more than two aspects, but like I said, there's one part where, you're building the drone, you're fitting the components together such that it works, right? And then the other thing is, how do you design like control scheme in order to get it to do something interesting, right? Because for drones, there's so many good uses for nowadays where like you have ones that have a camera attached. It's just for capturing videos, right? So you have other drones that can be used for like reconnaissance. You have other drones that can be used for like, actually doing something physical, like picking up objects, things like that, right? And then that's going to influence your choice of components in terms of like the order that you choose, things like that. So I would definitely think of like, how can that apply in a novel way? Just because people have built drones before. That's not new. But how you use the drone, I think that'll be kind of the interesting.
One of the things, the direction I was heading in the sentence, they call the search and rescue, and the ability to have an autonomous drone basically find someone.
Sure. Yeah.
In that setting, lost hiker or something of that nature.
Yeah.
And I'm thinking outside, it's easier. You're not limited by the indoor aspect. That'd be insanely difficult.
Yeah.
But mechanically, that to me, when I hear that, automatically I start thinking, okay, what kind of software do I need? How do I need to wire this thing? And that automatically sounds more like computer science, software engineering than it sounds mechanical engineering. Because at the end of the day, mechanical engineering is where's it going? I need to make sure it can withstand that.
Yeah, I mean, there's still a significant mechanical portion to that because because then the questions you might ask is, how long would a drone have to be active for like a search and rescue, right? And that's gonna affect, your power supply, that's gonna affect things like your motors, like how fast does the drone need to go? And so all of it is kind of a marriage together of like mechanical and electrical and computer components. So, so I think there's still plenty of mechanical engineering.
Okay, so it's not like I'd be limiting myself. My biggest fear was I don't want to get so into drones that I limit my experience that I limit myself essentially so I don't have the experience to apply to like a defense company or something that has to do with more structural design of an aircraft or something.
Gotcha. I think there's more than up there that you can apply because no matter what you're designing, I think drones are fascinating because you have to bring in so many different components.
Yeah.
Right. And I think that's not all that different from like an airplane or rocket. I mean, airplane obviously you have way more components, but I mean the idea of getting different like motors and the propellers and the chassis for the drone. Power supply, getting all of that to work, and then still working with the constraints. We want the whole thing to weigh less than this, right? That's not all that different from how an airplane is designed, right? Because an airplane, you have all these components that you want to stick in, but you have to work within your constraints too. And think about the application. So yeah, absolutely. I think those skills apply to very generally to a lot of different engineering.
Got it. Okay. And this could easily turn into a long conversation, but that was just in researching, seeing that there are search and rescue drones kind of already out there, autonomous search and rescue drones. Anything that seems unique seems like it would be limited more on the software engineering side.
Sure.
And there's not much innovation to be brought in from the mechanical engineering side.
I would disagree with that because I think a lot of probably what's out there are commercial drones that are very expensive.
Yeah.
And so there's always a sense of innovation of, can we make this thing that, it exists already, but can we make this from like commodity parts that are,
3D printed.
Yeah, more widely available for people, right? That's always going to be valuable.
Okay. So that you're not stuck with the company and you need to buy a $5,000 drone.
Exactly.
You can buy maybe a $1,000 drone.
Exactly. I think there's always going to be a market for that. There's always going to be innovation in that sense, right? Because you're working with way more constraints. And even if there are things like that out there, right? When you're working in that space of like, low cost engineering, devices, there's so many different ways you go. So whatever you come up with is probably going to be unique compared to what someone else can come up with. And yours are going to have unique strengths that maybe another low cost option does not have. So, yeah.
One of the other ideas that was bouncing around the group was an autonomous drone, semi-autonomous drone system to act as a rapid response drone for law enforcement in the case of a shooter scenario, something like that. Well, I've been in the military and I've been a cop. I thought of that and immediately I thought of legal. I didn't think of